We're almost finished with the special theory of relativity, but before we get into the last lecture in that topic, I want to go back and review a bit from your grade 11 physics course. Now, the page references you see on the following slides all refer to the Nelson Physics 11 University Preparation textbook, which I do not have a license to share with you. So if you are in your school and you ask to see that textbook, you can refer to those pages. However, we're not going to go as in-depth as you did in grade 11. We're just going to kind of cover this a bit more briefly. The reason why I do go through this is because I want to, it's always good to go through a refresher, and I just want to make sure that everybody's working from the same knowledge base. So we'll start with not nuclear fission and fusion. We'll actually start with radioactive decay. And what you would have learned, just let me get this in order here. What you would have learned regarding radioactive decay would have been about alpha, beta, and gamma decay. So we're going to have to go through that again, because that'll help you understanding both, in terms of this unit on modern physics, it'll help you understanding both the quantum mechanics lessons that we'll do next, and the special relativity lessons as well. So in terms of radioactive decay, I'll read through this slide and then I'll discuss. So you probably remember from your grade 9 and 10 science classes that a chemical reaction is the interaction of substances to form new substances. In a chemical reaction, the elements do not change. So when we have a chemical reaction, if you have carbon and hydrogen and oxygen interacting, for example, the carbon element does not change at all. It's still just a carbon element in terms of the fact of its mass, the amount of neutrons it has, the amount of electrons it has, the amount of protons it has. It's still a carbon atom. But nuclear reactions, they involve changes of the nuclei of atoms, and they can result in completely new elements. And when that happens, we have what's called a transmutation. So what you're going to see in this lecture is not chemical equations, but nuclear equations. And they look very similar to chemical equations. Now, when we have a nuclear reaction, there's terms that we'll use quite often is a parent atom. This is usually denoted with a capital X. That's the reactant atom. And we have a daughter atom, which is a capital Y, and that's the product atom. So it's kind of on your nuclear reactions, the left side you'll have your X, the right side you'll have your Y, and your arrow will be pointing from left to right. So you can write this down. A nuclear reaction involves a change in the nuclei of atoms. It sometimes results in new elements, which is called a transmutation. It's represented using a nuclear reaction equation, where the reactant is the parent atom, signified with a capital X. The product is the daughter atom, signified with a capital Y. And that capital Y isn't yttrium. The capital X is not any other element, because there is no element that has a capital X. So a little bit of history here in terms of radioactivity. It was in 1896 that Henri Becquerel observed that radioactivity is a naturally occurring event. When he had a sample of uranium and he placed it on top of photographic film, and then he saw that that uranium left an image on that photographic film. So radioactivity is it's the spontaneous emission of radiation. What this uranium was doing was it was emitting electrons, and that emission was causing the photographic film to, or is causing an image to be displayed on the photographic film. And the process by which a radioactive atom spontaneously breaks apart is called radioactive decay. It's always accompanied by the emission of particles or electromagnetic radiation. So either particles like electrons are being emitted, or other types of particles, which we'll get into, or EM radiation, electromagnetic radiation, is being emitted. So you can copy this down here. Radioactivity is a spontaneous emission of radiation, and radioactive decay is the process by which the nucleus of an atom spontaneously changes, and it's accompanied by the emission of particles or EM radiation. So it says here, Becquerel's accidental discovery of radioactivity encouraged scientists to seek ways to induce similar reactions using various materials. These efforts helped other scientists like Ernest Rutherford and James Chadwick develop a better understanding of atomic structure at the nuclear level, and formed the basis for the broad range of nuclear scientific work that followed. So now we're going to get into some of that work that followed. Specifically, we're going to talk about alpha, beta, and gamma radiation, because you'll have to know these, and you'll have to know the distinction between them. I won't read this slide directly, but basically what happened was it was noticed that certain types of radiation could pass through certain materials. So, for example, alpha radiation was a type of radiation that was stopped by something like a paper. I think it says here it's a thin sheet of aluminum. Beta radiation would pass through that thin sheet of aluminum, but it would be stopped by other thicker sheets or other types of other types of materials. And gamma radiation would pass through anything except for very heavy things like lead. So gamma radiation is what we call the most penetrating type of radiation. And then you may have heard of alpha, beta, and gamma radiation, but you might not know exactly what they are. And we're going to get into what they are on each of these subsequent slides. So alpha radiation is the emission of an alpha particle. And the alpha particle, you can see that big HE, is actually a helium atom. And I should also mention now, when we see these written here, you see AZ on the left and then the X. The A is our atomic mass, the mass number. The Z is our atomic number. And that A is always rounded. So in this case here, X can be anything. So this is the formula for alpha decay. It's any element, any radioactive element, that is. Y is the element that is has a mass of 4 less than X and has a number of 2 less than X. So for the example given here, you see it says Pu-240. That is plutonium, and its mass is 240. So it has 94 neutrons, 94 protons, 146 neutrons. So what happens with that is it has as it undergoes alpha decay, it loses a helium atom, which causes the entire mass of the plutonium to change by 4, and that basically means that there was a drop of 2 protons and 2 neutrons. And if that plutonium drops by 2 neutrons and 2 protons, it moves to the left on the periodic table, and it becomes uranium-236. So you're going to need to use a periodic table for a lot of these questions, which is why I've brought one. I have one here that I'm going to show you. You can find this on ptable.com. It's a dynamic periodic table. Now what was basically happening is we had uranium, and you can see that uranium's mass is 238. But in our sample question, we're working with plutonium first. So you can see that plutonium has a mass, it's in brackets of 240, it's 244. But our question here says it's plutonium 240. So let me just go back and show you. It was Pu 240. So that is our what our question states, and that plutonium ends up losing a mass of 4. The 94 becomes a 92. So it becomes uranium 240, because its mass is now 240, and uranium is, of course, the 92nd element. And what's left over is the alpha particle, the helium, and it has a mass of 4, and its atomic number is 2. So that's alpha decay. Beta decay is a bit more complicated because there's actually 3 different types. And that actually, going back to alpha decay, this partly explains how alpha decay is not as penetrating. It's not as penetrating because that alpha particle is a helium atom, and the helium atom is relatively large compared to what is a beta particle, which is in some cases it's an electron, but in all cases it's something similar in size to an electron. So beta negative decay is shown here. This is when we have our parent atom, and it increases in atomic number. So the Z increases by 1. This causes, this happens when an electron is emitted. And we can see a sample here of hydrogen 3. So the hydrogen 3 ends up emitting an electron. It still has, or rather, instead of having 1 proton and 2 neutrons, it then has 2 protons and 1 neutron, and becomes helium-3. So this is our beta negative decay, when an electron is emitted. And the electron is called the beta particle. Next we have beta positive decay. This is when not an electron, but something called a positron is emitted. And a positron is something that has the same mass as an electron, but has a positive charge. So the example here that's given is carbon 11. When the positron is emitted, it moves to the left on the periodic table, so the Z is decremented by 1. So carbon becomes boron. And then lastly, we have electron capture. So this is another type of beta decay. This is when we have an electron being absorbed by a particle, and when that happens, it ends up decreasing the parent atom in number by 1. So the daughter atom is 1 to the left on the periodic table. In all cases, in beta decay, the atomic mass, remains the same. Here's beta negative decay. A is the same on X as it is on Y. A is the same on X as it is in Y for beta positive decay. And for electron capture, A is the same as it is for Y. So let's just go through these three examples on the periodic table, starting with our first one here, which was H3. So H3, which you'll learn later is called tritium, if this gives off an electron, it will essentially increase in charge to become helium. And when that happens, the electron is the beta particle that's emitted. The daughter atom is now a helium atom. The second one we saw was beta decay that's positive, and this was when we had C11 become B11. So carbon 11, if it captures, if it gives off a positron, it would essentially decrease in charge, and it would move to the left and become boron. And that last one we had was an electron capture with a nickel 56. So if we had nickel 56 and it captures an electron, because an electron's negative, it would be moving to the left of the periodic table. It would become cobalt 56. So those are the three beta reactions, beta decay reactions. The last one is kind of the easiest to because it doesn't involve that much movement here in terms of changing. But gamma decay, the one that is most penetrating, actually involves the emission of a photon or energy. And what this helps explain how it's the most penetrating. Because while the helium alpha particle is quite large and can't pass through many things, and the electron, although it's small, it still has a measurable mass that means that it would hit certain objects and not be able to pass through them. The gamma decay, giving off of a photon, which is essentially EM radiation, can penetrate through many things. So here we have a gamma decay reaction. We have helium-3, and it decays to helium-3, but it gives off a photon with a 0 for the mass and a 0 for the number. So this is our gamma decay. So what I'd like you to do is copy down this slide here. It lists the three forms of radioactive decay: alpha decay, beta decay, and gamma decay. Gamma decay, we're going to focus on helium-3 gamma decay because this is essentially how it occurs. So that's why you don't see the X or the Y, the parent atoms or the daughter atoms for that one. Also write down the names for the different types of beta decay as well, which are electron capture, beta negative, and beta positive. I'll just continue on here. So in this case, we are asked to write down these different types of decays, and I will explain these kind of as we go. So Americium 245 is the first one that we're looking at. We're asked what would happen if this undergoes alpha decay. So if you remember alpha decay, we have to decrement the atomic mass by 4 and the atomic number by 2. So how you would do this question is you would start by, you'd write down your 245 AM95 as you see on the left. You'd put your arrow, and then you can write your 241 and your 93, Then you would have to go to the periodic table and look, where's my 93? 93 is this element over here. It's neptunium. And then for neptunium, I can write down the NP, the symbol, and then I write my alpha particle, which is the plus 4,2 helium. So then I can write my my NP for the neptunium, and then I can write my plus 4,2 helium. That would be my alpha particle. Okay, the next one here, I'll show you on paper. Let me just alter the size of this so that I can fit it on here. So here, we're asked to undergo beta decay. So if I was writing this out, it's selenium 81. So I'd write my 81 Se, and I have to find out what is the number, the atomic number of selenium. So going to my periodic table, I can see that selenium is over here, and the number is 34. So if my number is 34, I write down a 34 here. I put my arrow, and I have to, it says to undergo beta negative decay. Beta negative decay is the loss of a positron. So that means that my Y is going to be, have the same atomic mass, but the number is going to be 35, because the positron, oh sorry, I should be saying electron. The electron is going to increase, that's going to basically make it move right on the periodic table. So what I can do now is I can go back to my periodic table, I can find selenium, and just move one to the right, and I have bromine. So this becomes bromine. Next, I have to write my beta negative, or my beta particle, which in this case is an electron. So an electron is represented with a 0 for its mass and a -1 for its atomic number. So I don't know if that helps with me writing it down like that, but the next question we'll go through. Strontium 90 undergoing beta positive decay. So this is when we add a positron. The symbol for the positron is shown there. It's 0 + 1 E. It's shown as a +1, just to sort of designate it as different from being an element. So a 1 would imply that it is it might imply it's an element. So and strontium 90, of course, we go to the periodic table, we find strontium to find its number. Strontium is here, so it's 38. So it's 90, 38 SR. We know that the 90 is going to stay the same, but it's going to lose a number in terms of its atomic mass. Sorry, its atomic number. So it's going to become rubidium. So we write rubidium, 90, 37 rubidium, and then plus that positron. And then lastly here, showing electron capture. This is when we have it written on the left side. So we add the electron to our potassium 40. Sorry, I should switch this. So we add the electron to our potassium 40. And we're left with argon 4018. Because we move left on the periodic table, which I'll show you here because it does actually jump to the other side. So if I go from potassium and I move left, I go all the way over here to argon. So that's it for radioactive decay. We're going to move into nuclear fission and fusion next. So here it says, when Ernest Rutherford split the atom for the first time in 1919, few would have predicted how profoundly our world would change. The footprint of the nuclear revolution of the 20th century can be found in areas ranging from medical advances to nuclear power to devastating weaponry. Many nuclear reactions can only occur when particles are traveling at high speeds near to that of light. So a cyclotron is a device capable of accelerating particles to these very high speeds. High energy physics is the study of these interactions. So we have two types of nuclear reactions. The first we'll talk about is nuclear fission. And this is when we split an atom into two smaller atoms and we give off energy. So the image here is shown. You have a neutron, and it is hitting a uranium-235 atom. That uranium-235 splits up into krypton-92 and barium-141, and it gives off some other neutrons and energy. So this is our this is a nuclear fission reaction. There's some talk here on this slide that talks a little bit about the economics of nuclear energy. That's not really that important. In fact, the next few slides are not that important as well. What we're going to do is we're going to skip over to this slide here, where I want you to copy down the definition of nuclear fission. This is a reaction in which the large nucleus of an atom is split into smaller pieces. So this, imagine if we had instead of our product daughter kind of relationship, we can treat our product or our reactant, product is what I was trying to say. So our reactant is the XY. That's going to be broken up into its X and its Y, and it's going to give off some energy. So please copy that down. Next it says here, a reaction in which two small atomic nuclei fuse together to form a more massive nucleus is known as nuclear fusion. And the example given here is hydrogen-3 and hydrogen-2 being moved so close together that they fuse into one atom, which becomes helium. Another neutron is left behind and energy is given off. So this is the energy that powers the sun, which is our nuclear fusion reactor in the sky. Essentially what's happening is we have the sun is mostly hydrogen, but as that hydrogen gets pushed together by the pressure caused by gravity, those hydrogen atoms are moving so close together that they start to fuse together into helium. And when they fuse together, they give off a massive amount of energy. There's not really a way to harness fusion energy at this time. That's what this slide kind of talks about. But if you're curious, you could look some ideas up online about how some scientists are trying to do this. Because if they could, it would be a massive amount of energy at our disposal. But copy this down for nuclear fusion. Actually, only copy down the first point. So it's a reaction in which two small atomic nuclei fuse together to form a larger nucleus. So this is when we have an X and a Y, and those are our reactants, and our product is the XY together plus energy. This slide here talks about some of the ways nuclear fusion can be put together, but we're not going to talk about that. So now this gets us to the famous equation in physics, E equals mc squared, which is essentially an equivalence of mass and energy. And this is why we need to understand this well in order to do our next topic, which is what does mass energy equivalence look like in the world of relativity. But going back to non-relative understanding of mass energy equivalence, Albert Einstein proposed this equation that energy is equal to mass times the speed of light squared. And this was a very difficult thing to understand at the time, that energy and mass can be related. What it actually means is, in a nuclear reaction, what we'll find is there's a loss of mass. And that loss of mass is referred to as the mass defect. That mass defect plugged into this equation is equal to the energy that's given off by the reaction. So I'd like you to copy down what's in this green box here. This is the law of conservation of mass energy. It says mass can transform into energy and energy into mass, such that the total mass energy in an isolated system remains constant. And I'd like you to copy this slide down. E equals mc squared is Einstein's equation. E is the energy in joules. M is the mass defect in kilograms. C is the speed of light. And that's a constant 3 times 10 to the power of 8 meters per second. I'd like you to copy down the note as well. It talks about the atomic mass unit. And the reason why this is important is when you look at your periodic table, you'll often find that you will find that the atomic masses that are given are actually values measured in atomic mass units. So, for example, if I switch over to my periodic table here, and I look at platinum, I see a 78 here. Actually, I'll just do it with chromium. I see a 24 here, and a 51996. That 51.996 is my mass in atomic mass units. If I want to convert that into kilograms, I have to multiply by this value here, which is 1.66 times 10 to the negative 27. So let's look at how this is used. And these are kind of, they seem like very difficult questions, but they're not really, they're not as hard as they look. So I'm going to turn this on. And what we have here is an equation, a nuclear reaction equation. And for this, we're asked to find what's the mass defect and what's the energy yielded from this reaction. Now, one of the questions you'll get is if the reaction is a fusion reaction or a fission reaction. What we can tell is if we have something that's large and it breaks apart into two smaller things, it's a fission reaction. So here we have uranium-235. It breaks up into cesium-140 and rubidium-93. So this is a fission reaction. And for these questions, you'll also be given the mass of different the different components, or you'll be asked to find them on the periodic table. So the mass of the isotopes here are given. So uranium-235 has that mass of 235.044 U, and cesium-140 has a mass of 139.909. Rubidium-93 has a mass of 92.922 U. What we have to do to find the mass defect here is this equation here, which I want you to kind of write down here. Mass defect is written as, MD, with a capital D. So mass defect, right, is equal to the mass of the reactants minus the mass of the products. So MD is my mass defect. I'm going to copy this in your notes. M is the mass of the reactants. M reactants is the mass of the reactants. M products is the mass of the products. The reactants are on the left side of our nuclear equation. The products are on the right side of the nuclear equation. So for this question, my MD is my mass of my reactants, which are, I'm going to write down Mu plus Mn for the neutron, minus the mass of my products, which is MCS plus MRB plus 3 Mn. because we have 3 neutrons on the left side. So mu, I will write down everything. I'll keep in atomic units until I'm ready to convert at the end. So 2355.044 U plus 1.009 U minus 139.909 U plus 92.922 U plus 3 times 1.009 U. So I end up with a mass defect of 0.195 U. Now, what I should do is report my mass defect in kilograms, unless I'm asked to leave it in this form. So to report it in kilograms, MD equals 0.195 U multiplied by, and just so that we recall, 1 U is equal to 1.66 times 10 to the negative 27. That's kilograms per U. This cancels out my U here and here. So I'm left with 0.2. And in this case here, I'm going to record it with, if I look back at my givens, I have 3 significant digits in the in my conversion from 1U to kilograms. However, because these questions require a fair deal of accuracy when we're working later on, what I want you to do is report your answers using up to 3 significant digits. So this is going to be, sorry, I should say up to 4 significant digits. So this is going to be 237 times 10 to the negative 28 kilograms. So that's we're writing it this way because we when we're dealing with these mass defects, some of these values that you'll see are measured quite accurately, like the mass of uranium-235. So we need to keep that accuracy by keeping a fair amount of digits past our actual significant digits. So that is my mass defect. Now to find the energy, E equals mc squared, where m is the mass defect. So E equals 3.237 times 10 to the negative 28 times c squared. So it gives me an energy output of 2.913 10 to the negative 11 joules. And in this case, because I'm reporting an energy, I can actually report this with the 3 significant digits. So basically, our answers are this value here and this value here. For mass defect, use a minimum of 4 SDs. And for the energy, it's pretty much always going to be 3 SDs. So I'll just write down 3 SDs for significant digits, but it could be, could possibly be less, although it could also be more. Most of the time it'll be 3 SDs, but when you're doing your mass defect, always use a minimum of 4 significant digits. Let's try another one of these questions. This time, we're going to look at it and try to figure out, is this a fusion? Or, well, it already says it's a fusion, but we're going to figure out why it's a fusion reaction. So looking at this equation, we see that we have a hydrogen and a hydrogen. They fuse together and form a helium. Because we have two smaller things becoming a bigger thing, we have fusion. And the H2 is commonly called deuterium. H3 is commonly called tritium. So let's move over to this side here. Let's figure out what our mass defect is. So our MD is our mass of our reactants minus the mass of our products. I'll slide this up a bit here so we can see it better. So our mass of our reactants is the tritium and the deuterium. So this is going to be 2.014U plus 3.016U minus my helium, which is 4.003U, and my neutron, which is 1.009U. And my energy doesn't factor into the mass defect because my energy is the remaining mass. So I have a mass defect of 0.018U, and when I multiply this by at this point I can convert, so I'm going to multiply this by 1.66 times 10 to the negative 27. So times 1.66 times 10 to the power of negative 27. Should be negative 29 when I'm done with it. We have 2.988 times 10 to the negative 29 kilograms. And that, we'll report that as our answer. Oops, I didn't circle the kilograms part. The next thing that we would do is convert this to energy. So fit it in here. E equals mc squared, where E equals 2.988 times 10 to the negative 29. Multiply this by c squared, which is 3 times 10 to the 8 squared. Now I round to the original 3 significant digits that I had, and that 3 significant digits is based on my 1u equals 1.66, if you're wondering where that comes from. So 2.69 times 10 to the negative 12 joules. C squared can also be written in mega electron volts per U. This makes it a much more convenient measure. We won't do that, just to kind of keep it a bit easier, but keep that in mind. There is another way to convert that to use your energy. So we're going to do this question, this last question, and we're going to do it with a, we're going to do this using 1.66 times 10 to the negative 27. So we're going to convert it, we're going to convert it to kilograms, and then we're going to convert it to energy in joules. But just be aware there is another method. So let's turn this on here, and I'll move this over. Okay, so now okay, so we're given a stellar fusion reaction. So some suns actually, after this is another kind of curious thing, after a sun burns up all of its hydrogen, it's left with helium. So first it's a hydrogen fusion reactor. Once there's only helium left, it starts to burn up that helium. And that helium gets fused together in this arrangement, where it's three heliums fused together to form a carbon. So our stellar reaction here is the mass defect is calculated the same way. MD is equal to mass of the reactants, subtract the mass of the products. So the mass of my reactants is 3 times my mass of my helium, which is listed as 4.00260 U. My mass of my product is 12.00000 U. You could see that some of these things are very accurately known in terms of their measurements. So 3 times 4.00260 subtract 12 gives me this value for my mass defect, 0.0078 U. And I'm going to convert this 1.66 times 10 to the negative 27 kilograms. So I multiply this by 1.66 times 10 to the power of negative 27. And I'm left with an MD of 1.2948 times 10 to the negative 29 kilograms. Now I'm asked to find the energy released from this, and I'll do the energy using E equals mc squared. So E equals 1.2948 times 10 to the negative 29. Multiply this by c squared, which is 3 times 10 to the 8 squared. So, which is the same as 9 times 10 to the power of 16. That gives me this value here in energy, 1.17 times 10 to the negative 12 joules.